so today we want to see two things. One is, you remember that the last class we cannot, recover some suppressed carrier amplitude modulation. So because we don't have any phase or frequency recovery. So today we want to talk about that. And also, there will be like two lectures. The second one will be about FM modulation. So we will try to run the lab that corresponds to this class, and also, if we have time, the lab related to the FM. So maybe today we are a little later, but we will try to stop at 8 anyways. Okay. So basically, the problem that we have already is that until this time we are making like the tuning by ourselves, just looking on the spectrum and see how much is the offset, and try to correct that with the board. But that is not the way to do it. So the idea is to try to see how this frequency correction here it should be done automatically. Okay. So let's say on the common channel we have two problems. Okay. So you know that we always will have some propagation delay. So if these two oscillators are, let's say, rubidium or atomic oscillator, anyway we will have any delays here, so the phase will be not the same. And of course they will not be atomic oscillators, so we will have some frequency shift. So that's two problems will happen always, and we have to deal with that two problems, okay, in order to try to recover our signal. So, well, this is going to happen on the phase shift, okay, because of the delay. It's really simple stuff. This is a little more complicated. That when let's say in this case, if there is a mobile phone that is moving, when there is moving to the let's say base station, these guys want to see like this guy is increasing the frequency, and when that guy is moving far away, it's like reducing the frequency. So these guys will think that it has a frequency offset. Okay, so this guy needs to try to correct, and also that guy too. Okay, so you know that is the Doppler effect. Okay. So this is a very simple simulation that, well, I exaggerate a lot because it's like 5,000 ppm the error between the two oscillators. So if you say okay, the frequency is 100, so because it's 500 ppm, it could be 99.5 or 100.5. So they will start synchronous, but at the end, of course, there will be this phase offset. This is just simple simulation to show you what happened with the phase offset. So we remember that we have this, okay, on the dual sideband suppressed carrier. That was our modulator, and ideally we want to demodulate exactly in the same way that we make the modulation, but the problem that we have this error here on the signal, okay, on the frequency. So the idea is that instead of having this, well, we need to try to have something here. We need to try to have something here that give us the correct frequency. Okay. So that's why I say option 1 there is doing the transmit carrier. We know that on the transmit carrier we don't have any problem, but the problem that we have is we spend a lot of power. So you remember that we spend a lot of power on the carrier, and the carrier is not information. Okay, so the better way to do this, of course, with some carrier and frequency recovery. Okay, so if this is our, let's say, transmit signal, and we follow this, okay, we are making the modulation here. So if we follow the math, we know that the high frequency terms will be filtered out. Okay, so at the end will be this one. With this error here will be the error between this carrier and this carrier. Okay, so that will happen on a real case, no ideal case. So this is again a review. You know or you should know all of this, but we will try to make a review because we will implement the PLL. We are not going in deep of the parameter of the PLL, like all the games that you have to take into account, the bandwidth, etc. But we are just, I will just give you an idea of what we are changing on the PLL and how you will implement that PLL. Okay. So basically, as says here, so you can see like three parts. So one will be the phase detector, the loop filter, and in our case will be an NCO. So this is, voter control oscillator, but this is numerical control oscillator, okay? Because we are on the digital world, not on the analog one. So basically, we wanna talk a little bit about how these blocks work. But basically, as you can see, these guys will receive some error signal, okay? And you know that in the case of the VCO, what it does is it changes the frequency according to the change of the amplitude, okay? So, and the NCO is more or less the same. So basically this guy will give me the reference that will try to follow this. And this phase detector, at the end, we will get something like this. That will be something proportional to the phase difference. That is what we know, that we want, okay? To see what is the phase difference on the two signals. And then filter that, because here will be some high pass filter. Sorry, this is a low pass filter, will be some high-end component that this guy will filter, and well, this is how this works. But we wanna start looking in detail each of the blocks. Okay. Okay. As I say, the phase error is proportional to the phase difference. So remember that. Usually, this is implemented in let's say digital is implemented as a multiplier, but on a physical world you can implement this with a mixer. Okay, if you have a mixer and you mix the two signals, at the output you will have the phase difference of that two signals. Okay, so what happens when you, let's say, mix these two signals? So if we follow the math, we have this. Okay, this is the incoming signal. This is our reference. This high pass component is the one that the filter, the loop filter will filter out, okay? So that's why we cancel it here. So at the end, we will have this low frequency term, and when the difference here, or the angle, so the sine of the angle is really small, we can approximate the sine of the angle to the angle itself, okay? This is trigonometry stuff. So that's why this approximation. So at the output, we will have this, okay? Always if this difference is small, okay? So, and of course, when the PLL is locked, that difference is always small, okay? Then we have the loop filter. Basically, we will have like different type of loop filter. We always have one integrator that is placed there by the VCO. And then depending on the number of integrators that you have, so if you have one more, so in total you have two, that is a PLL2 and PLL3. Usually you should work with this guy, okay, with a PLL2. If you are working with GPS signal, you will see that you want to work with a PLL3. That's something that
I have.
Yeah.
So I'm just curious, why do you have like two loop filters? I mean, what is the difference between having one loop filter and...
You will see, so the difference in these loop filters is how many integrators they have. So
this comes with like better performance?
Yes,
oh.
Depending on what you want. Okay, what kind of signal you want to change. Okay, so that is one of the things that we will see right now. So depending on how is your frequency changing, how fast, or what is, if this is just a step or a ramp or another kind of changes, is the PLL that you have to use. Okay. But what I'm saying is that usually type 1 is, you will see that nobody uses type 1 because they cannot follow too much changes basically.
Okay.
Okay. But we will see this a little later. And finally, so we saw the phase detector, the loop filter, and then we will have this bundle VCO or NCO. Okay. So basically this signal is the filtered signal, okay? So it's basically something proportional to the difference of the phase. So these guys want to integrate this signal, and we have some estimation of the instantaneous phase, okay? So depending on that instantaneous phase, it will create an output, okay? That could be sine and cosine, could be both, or just could be one. So, but basically, remember these signals are the ones that we want to use to make the down conversion, okay? Well, but really, what we will use is this guy. Okay, it's a numerical control oscillator that is just the digital expression. So you could see it's just we replace t, so continuous time by discrete time, the integral by this summatory stuff, and the estimation will be the previous one, some plus some factor here that we will see how that factor affects. And on the design, you should be too careful about that factor that is just a step. So if you can, forget for now about this, if you could see here, basically, if you have a fixed step, okay, and you give this step to a cosine function, basically, for example, this is n over 6 and this is n over 12, so the red and the blue one, and of course, because this n over 12, this small step, it will create a cosine that is lower frequency than this guy, okay? So, take a look on that. And basically how this affects the frequency that we could create, okay? How accuracy we will have when we create that frequency, well, depend on this formula that is basically the desired, this d is the desired frequency that you want to synthesize, and this is the sampling frequency, okay? So remember that.
So
yeah.
Mu is constant, is fixed?
Mu is, there is some, we will see that mu is have some fixed part that is constant,
yeah.
Okay? That fixed part will be the frequency that you think, so you are transmitting at 1 G, okay? So on the receiver side, say, that guy is transmitting at 1 G, okay? That step will be related to that frequency. There will be some fixed step that will create 1 G, okay? And then we want to add some variable step. That is the one that is trying to follow the phase changes. That one will be variable. So this guy has two components, okay? One is fixed and the other will be changed, okay? So, well, here is your more or less will clarify your question, okay? So basically you have, let's call this be the error signal, okay? This error signal will be moving up and down, okay? So we have some constant that will multiply this, so this factor is the one that is changing, okay? This one is the quotient frequency, or call it the base frequency, okay? So this one will be fixed. It's just a number that is there and it's always the same, okay? But this guy is changing, okay? So that's why this mu have two factors, okay? The fixed one and the one that is adapting to the phase, okay? Here you have the integration part, okay? And finally the sine and cosine of that two guys. So here is the integrate. Okay. Some of this theory, it looked weird from you, or is something that you don't remember, or is something new? I mean, BLL stuff. You make some, I don't know, at least paperwork exercise with this or not, or you don't remember? Okay. Oh, you don't remember? I hope that you don't remember, because you should see this on some digital communication course or whatever. Now I want to go, this is important, because sometimes when you start playing further with this, not just how we are playing right now, and you want to go inside the FPGA to create some reference signal, for example, you have to deal with this, how they call it DDS. Okay, DDS is Digit direct digital synthesizer. But basically, DDS is an NCO, okay, that you wanna modify. So basically, inside the FPGA or in a digital way, to say in some way, how you create this sine or cosine. Okay, it's quite simple. Okay, inside the FPGA you have these lookup tables, or call it RAM memory or whatever, FIFO. Call it whatever you want. That is, the name is lookup table, but imagine that this is a FIFO, and you save there, okay, all the sine or cosine signal that you wanna send it out. Okay, basically this is how it works. And here you have your accumulator that will be, sending out each of that samples with some clock that you will have. Okay, so the number of bits that you have on the accumulator, it will depend on how big will be this. Okay, maybe I could try something here. You are okay. Let's make this work. Oops. Okay. Basically, imagine this like a FIFO. Okay. Okay. And here you have some counter, or call it accumulator there, but it's the same. So this will be 1, 2, 3, 4. Okay. And here you will have, let's say, something like this. Okay. So here you will have this value. Here you will have this value. Okay. So this is the deep. Okay. The deep of this memory, and that deep is 2n. Okay. So that's why I'm telling you that depending on the n bits that this guy has, okay, is how deep this will be. So we will take a look of how much this deep affects on the frequency that at the end I will create, okay, and also we will see how much if I increase this, how that will affect on the frequency that I will create, okay. So that will be the L bits, okay. So that's it's related to the amplitude resolution. Okay, this will be L, okay, and this will be N, okay, sorry, like N, that is 2 up to the N, okay. So these are the things that's saying there, okay. Then you can take a look. Basically, this is the table that I was trying to draw there. Of course, that it's better there. But as you can see right now, that's depending on how many locations you have. In this case, it's really short. It's 16. Okay. It will depend on these steps. Okay. So you could clearly see that depending on these steps, it will be which is the frequency that you could create. You cannot create whatever frequency. Okay. So if we want to create whatever frequency, well, we have to take care of this deep memory. So this is just to let you know that nothing is free. Okay, everything will take some resource inside the FPGA. Okay. So, and also the other was related with N. This is related with L. Of course, if we have 8 bits, for example, this is the, let's say, the black one here is the real, and the dots are the quantity size. And of course, in this case, well, this signal will be quite awful, and this will create at the end the two problems. Let's say the short N indeed, or very short L. Both of that will create a tone. When I say a tone or a frequency, that will have really bad spurious-free dynamic range. Okay, and that is a big problem for our communication stuff, and we will see why. Okay. So basically, just to give you an idea, you have only this saved on the memory. So you go with your counter and you will giving out these values, and then the counter overflow, and again you go to the beginning and read all the memory, and that is how the DDS works. Okay. Of course, if you increase the clock of this counter with the same memory, everything is the same, you will create a high frequency. Okay. That's clear? Okay? Fine. If it's not clear, just let me know. I'm trying to explain another way. So here's some problems that we will have. For example, okay, remember that we say that on the previous slide we say that mu was 2 pi fd under fs. Okay, because this is 2 pi, but it's also n. That's why there you see that is n. Okay, fd over fs. Okay, and that is what is each of these things. So let's follow this example. For example, you have 8 bits. Okay, L is equal to 8. So then 2 up to 8, you have 246, and you have a sampling frequency of 10, and you want to create 2.5. Okay, you just replace that value there, and here's the result. Okay, so this mu value, okay, if I just want to create just one fixed frequency, that mu value should be 64. Great. Okay, but what happens if I want to create 2.4? I do the same. I make the maths here, but this value tell me that is 61.4. And you know that this is a digital counter. Okay? So this going 1, 2, 3. Okay? I cannot give them a discrete, a fractional increment. Okay? That's not possible, because you just want to count one by one. So the thing that we have to do is, okay, before to give the value to our counter, okay, let's try to do this. Okay, let's add this n will be the integer part, and this b will be the fractional part. So we will be adding fractional parts here in our accumulator. That is possible because it's just addition. But what we are giving to our memory, okay, will be just, it should be just this, okay, because the memory will not understand. Give me your position 1.5, okay, it's position 1 or position 2, okay. So doing this, let's say in this example, if we use the same 8 bits, okay, we're using 8, but now we'll say, okay, let's use 4 bits, okay. This is some design stuff that we are not going so deep. I'm just giving some idea how to choose this. But basically, with these 4 bits, you could discretize this number. That is not the same as this 44444 here, okay. But basically, if you do again the math here, this is the frequency that you could get. This 2.399. Okay, 2.399 is quite close to 2.4. Okay, so if you wanna get more 9s here, okay, well, you have to play with these two numbers, especially with this guy. Okay, and we will see what happens when we increase the length of n, l, or the fractional bits. Okay, so here is what's gonna happen. Okay, fine, we are making the accumulation on a fractional manner. So let's say if our increase here, the mu is 1.7. Okay, so first step with 0, 1.7, 3.4, and so on. Okay, so that will be fine. But then we are just taking apart this and just taking the real part. Okay, because we have to give again to the memory the real one. So this one will be the ones that is going to the memory. Okay, so this beautiful blue sign is not anymore. Okay, because we are reading 0, 1, and what happened with 2? We are not reading 2. Okay, so we are missing some value here. Okay, so again, that will create spurious frequencies. Okay, so our tone will be not that beautiful. So basically, that's a truncation error. Give us something like this. So these are some examples. Okay, let's say n is 6. Okay, And B, you see here B is pretty high, like 16 fractional bits, okay? This is just to show you that it's not about, okay, increasing the fractional part or increasing, it's just a mixture, okay, that you have to play with. And the L, so this number is 52, that is quite big. But, taking in account that if this is the memory that we have, okay, and if we just increase one bit here, it will be n times 1, the resource that we are increasing, okay? That's fine. But, if we are increasing 1 bit on n, okay, we will be double this frequency, okay? So, make sure what you are increasing. So this is, I guess, this next slide, okay? So you can see that here is the spectrum is a little better, okay? We increase, you can see we increase n double, so that's why it is double the size of the memory, and we have the same, let's say, fractional part, but L here is not, so this L is not too high, it's just 8 bits, okay? So it's very, let's say, simple digital analog converter, like 8 bits, okay? I don't have a DAC or a DAC that have 32 bits, okay? So you can see that this, it doesn't help too much, okay? What it helps too much is how small could be that mu, okay? That is what is helping us a lot. This is just to give you an idea on the first example. If you measure, basically, this is the spurious-free dynamic range that you have, 56. Just to give you an idea. GSM needs 110, okay, spurious-free. So if you want to receive some GSM signal, okay, your LO should be really pure, okay? Should be 110 dB of a spurious-free signal. So you cannot recover GSM with this, okay? And of course, forget about LTE, okay? So this is one of the really cool idea how we could play with this, okay? So if you remember one of the previous slides, we have 1, and then we jump to 3, and then we jump to 5, and then 7, and maybe something in the middle. So it's like we have a signal that is broke, okay, because of that truncation. So you know, in every signal processing, when you wanna broke some pattern, what do you do? What do you do when you wanna broke some pattern in a signal?
Sample.
Yeah, but you wanna just broke a known pattern. What? No idea? You add noise. This is something something that sometimes you say, okay, I am adding noise, but I am improving this. How that could be? Okay, that's happened. Okay, that's some weird stuff that happened when you add noise to the signal. So you broke that pattern. Okay, so instead of every time reading 1, 3, one time you will be read 1, but the next one, because of the noise that you are adding it, you will read 2. That is the one that you want to read. Okay, that is the idea. Sorry. So basically they call it, or the theories call it jitter generator. This guys is just basically a random generator that could be a BN sequence or some kind of another random noise generator. So basically, if you see this is the same that we had before, exactly the same, but we are adding a little more complexity, adding to this part of the fractional, we are adding some noise with this kind of jittering bit, okay? So at the end, this is the number that is going to the memory. So when you do that, in this case, so this graph is showing that this number of bits here on the jitter generator is exactly the same number. Let's say you have 6 bits here, this guy is creating 6 bits. Okay, this is some thing that always works. And with the same number as before, so no adding length or n or whatever, just adding this, you get a better, much better. So you improve like almost 30 dB, because the previous one was 30 and this is 50, so 23 dB. Okay. So all of this that I show you is just for telling that there is a block in MATLAB that you just place there and you configure and you are done. So you don't have to do all this stuff. Okay. But in order to configure this guy, you have to understand what I tell you. Okay. Because here you say, for example, Spurious free dynamic range. Okay. Frequency resolution, the mu that we wanna see. So depending on these two values, you could see here 100. Okay, fine. You could write wherever you want. 100, and then here 0.1. But then it will say, when you compile and try to place on the FPGA, it will say not enough results. Okay, because that thing that you want, okay, is really good, but it will take huge memory to do it. Okay, so that's why I'm trying to telling you the hardware part that is always related with what you did in software here. Okay. Well, by the way, this is the DDS compiler, and this is I don't know if some of you use. There is a tool in MATLAB that is called System Generator. Costas, guys, you should. I don't know, but previous guy for you was using this a lot. All the warp design are doing with System Generator, basically. What is System Generator? It's exactly the same as Simulink, but instead of placing blocks, let's say another or a multiplier or whatever, you place this exactly the same block, but at the end when you compile, that's translated to VHDL. Okay? So you make whatever is your system there, but all with this block from System Generator, and when you compile it will create a VHDL file, basically. So it's a tool that is really cool. Okay? Because you don't need to know anything about, let's say, VHDL. At the end you need to know something because you have to integrate that file on the FPGA, okay, to do your processing stuff. But what I mean is exactly the same of Simulink stuff, but it's hardware basically. So you are playing with real hardware there. Okay. So this is a good tool. Well, these are the 3 types of loop filters. Of course, this is not integrator, 1 integrator, 2 integrators. And I am not talking about how to design. There is a theory behind that, like, I don't know, a couple of pages on the book. So basically, we will have this, and for this work, we have to take a look on all these constants, because that constant will say how that PLL will work. So how fast? So this is some of your questions. Depending on this design, we'll see how fast that PLL lock, or what kind of signal this PLL can follow. Okay, if the, let's say if the phase offset is huge, this guy maybe cannot follow, or yes. Okay, that is called what is the bandwidth of the PLL. Okay, so that's depend on the parameters design. And just to give you some ideas to different behaviors on the different type of, let's say, loop filters or PLL. Basically, loop filters type determine the PLL type. So here is how this PLL will respond to a step. So let's say I have some frequency now, and then I have this frequency. Okay, that is the step changes, and this is how this guy will follow. Okay, you see, all of them more or less try to follow that step. This is how they will answer to a ramp. Okay, so instead of having a step like this, what you usually will have is something like a ramp. Okay, so your frequency will going up or going down, but it will move in like this. Okay, this is the most typical case. So that's why I told you that type 1 cannot follow, because it will have a stationary error there forever. But usually type 2 and type 3 can follow. And finally, this variation is called an hyperbolic variation. That happen is kind of related to the Doppler effect between the receivers on Earth and the GPS satellites, because you know the speed of this satellite is quite bigger related to someone that is moving here. That creates some phase changes that seems like an hyperbolic changes. Okay, so the only one that could follow that kind of variation is this type 3 PLL. So if you have to play some time with this, remember that type 2 will not gonna work there. And finally, this is maybe more related with control theory stuff.
Yeah.
All of this is related to control theory at the end, because it's a a feedback loop. So, but usually the factor that we will use for the damping factor will be something around this 0.7, because if we take a look on the different graphs, so the difference is the step, run, hyperbolic. So if you see 0.7 is more or less the one that have less error and answer much faster than the other ones. So that is another factor that you have to take a look when you design a PLL. So as I told you, we are not designing a PLL, but on the lab today, you want to see what is the behavior of the PLL. Okay, for example, this guy. So you try to take a look on this graph and try to tell me which guy will have a bigger bandwidth or a shorter bandwidth. Well, it's there, but anyways. So take a look on this. This is time, okay? Time and time. So we are comparing these two PLLs. Okay. So let's say that at the beginning, this guy, the PLL, have 1 megahertz. Okay? See? 1 megahertz. But the reference that is coming, the signal that I want to follow, is 0.99. Okay? So this guy will take all this time to try to adapt and then at the end follow the signal. Okay? So at this time we could see, okay, the PLL is locked. Okay? And this other guy, exactly the same, have 1 here, but you could see that it's much faster to catching the signal. Okay? But we will have a different, let's say, situation with this. As you say there, so if you have a very short bandwidth PLL, it will take longer to capture the signal. And the opposite. If you have high bandwidth PLL, in this case, okay, it's good because if you think high bandwidth means that this guy can track bigger changes. So if he can track bigger changes, it should be faster to track. Okay. But the problem that you will have with that, with this guy, you say, okay, let's do all the PLLs should be high bandwidth PLL. The problem that if you increase your bandwidth, you will also increase your noise. Exactly. So you will increase your noise and you will have also problems because more noise is going to your PLL. Okay. Enough talking about PLL. So this is related. So from the last class we saw that we cannot recover these Dulles high band suppressed carrier. Have a problem with that. So there is a way to recover because remember, suppressed carrier, there is no carrier there. So what we will follow if there is no signal to follow? Okay, because with a PLL you can follow some signal that is there. But in suppressed carrier, there is no tone there is no signal to follow. So, this is called Costa's loop. The guy that invented was basically Costa's name. And this is how this works, okay? So, you will have the signal coming here, INQ signal. And after this match filter, or we call it the RC filter, okay? Here is something that is not shown, that is like the decision device, because as you could see, this is an estimation. So what is this? Is it 1 or is it 0? What is? So some decision device should be there. And then you multiply these two signals. So this will be I and Q after making the decision. So if you multiply these two signals, it will give you something like this, okay? And at the end, this by trigonometry equality is this. What is the advantage of this Costas loop related to the PLL? The advantage is here, okay? So this guy have double. Remember that the other one is proportional to the cosine of the difference of the phase. That's it. This guy have a 2 here. So this means that this guy is more sensitive to the change. So it will amplify small changes. It will amplify by 2. Okay. So this is one of the advantage of the Costas loop. We will implement this on one of the lab to recover our dual sideband signal. Okay. Yeah.
There a factor there, so
Yeah, but this is amplitude. This is related to the amplitude. But what I am talking is about the phase. Okay. Remember that's what we care about. Forget about this because we don't care about this. What we care about is the difference of the phase. Okay. This is a real implementation on this is how the blocks on system generator look like. This is the symbol, of course, of silence, because MATLAB works with silence. I don't know if there is a tool from the other company that is Altera, but I work with this. And basically, as you can see, this is the theory, okay? This is what the theory tells us. This sign, okay, is the easiest way to make a decision on a, let's say, QPSK. You just take the sign of both and say, okay, this is 1 and this is 1. Well, this is symbol. This is 1 and this is 0. This is another symbol. Simple, really simple decision. That's why it says decision direct. And you make this. So here you will have the decision signal, and here you will have the other decision signal. So I and Q estimated, and then you multiply and make the Costas loop. This is exactly the same of that. So just to give you an idea how simple it is to play with this system generator. Okay? If you sometime have to develop something to run faster on the FPGA. Okay? If for sure, if you are doing some research at the end, you will try to play with that. And here is just like a full implementation on, again, on system generator of a 4QAM, but I will just talk about this part. So, if you see here, this IF mixer, okay, is the one that will receive the signal. Okay, this is simulating the ABC. Okay, you will receive the sample here, and here inside, of course, you will have a multiplier or a mixer to make the down conversion. The down conversion with which signal? So here, it's not clear to say, but maybe on the slide that you have, you could see clearly. This is another. Okay. So this is the mu factor that is constant. As I told you, it's a number. It's there. And if you follow this one, okay, this is just some kind of reset logic. So if you follow this one is the phase output of the Costas loop. Okay, that will give me the step by step what is the mu that I have to update at the end here inside. Okay, and well, create the frequency. We will go in deep on the next slides on that. So how you can do that. So, okay, this is the end of this one. So basically on the first part of the lab, we will run some examples like simulation, and also we will try to capture the previous signal that we cannot capture with this Costas loop, and you will also some PLL capture with the AM signal that you previous was using in the last class. Okay, and now I want to take a little of water and then continue. question, Winnie. You wanna take the pictures now, or you can wait like half an hour? Or?
I'll just do something now. Or
Okay.
Are you going to workshop in half an hour?
Okay, no, yeah, I just stopped here. So, well, she wanna take some pictures of you trying to show that you are doing something, just to go to the web. So just open the computers, plug the boards, open MATLAB, and open whatever module. So she can take a.
Don't open Blackboard. Open something like really sciencey and techy. Whatever that means.
So you can try to play with the demultiplexing stuff that we did last time, with that one maybe, and just try to show some signals on the screen.
Is this like for a class or is this?
No, it's conference room,
Oh, okay.
but we are using for classes.
Oh,
Yeah, but it's a conference.
okay. So this is like a voluntary thing that people come to just because they want to like learn more.
This workshop, yes.
Okay.
Yeah. Remember the that side. Yeah. So try to run the DMAX stuff, DM. One transmit, the other receive. She takes pictures. Well, in the meantime, maybe take the time. I bring today this board. This is an old one, pretty old, like 3 years, something like that. USRP, that is the analog board. The National Instrument board. You know that National Instrument bought this Etus company like 5 years ago, something like that. Okay. So basically, I bring it today to make a very simple example. Okay. Just to tell you that you just change the block on the receiver, and you have all your let's say communication stuff the same. Maybe we have to play a little bit with the sampling rate, because this guy have a fixed clock, so we cannot play too much with that. But at the end, you will see that with the same software that you have, you change completely the hardware because it's nothing similar. These guys run at 2 gigs, have fixed clock, it's an old version, totally different. And you will see that at the end, it will work. Okay? So just to give you an idea that all the things that you did, let's say in MATLAB, these guys use LabVIEW, of course, because LabVIEW came from National Instrument. But what I'm trying to tell you is that the software will remain more or less the same, no matter if you change the hardware. Let's say in the future, much better boards come and you get a better grade on the board or whatever, so you don't need to redo all your software again and again. Okay, so we want to play with this later. So, well, Brini, you're free to, I don't know, take some pictures.
Okay.
Try to run that.
Which one?
No, I'm saying
don't know
that
who's,
the
like,
one that
running
I
the
think these are
multiplexer
bots.
one. Let's say the
Yeah,
3 tone
you're
on
just
different
setting
band.
up things, yeah.
Oh, okay. Just like let me know when you guys are ready.
Yeah.
The last one that we made yesterday on Friday. I'll show you, or whatever you want. But
Here's one.
let's say this one. Or this one. So this one on the transmitter and on the receiver side. Okay. FDM demo, and the other is FDM transmitter side. Just open that and so she can see something on the screen. Which one? Which one is the bad one? No, I don't remember because
I think it was
I don't know.
but he's switching them
yeah,
every
I don't
time,
know.
so
It's
yeah.
like because I believe that this one. I don't know. anyways, look for the name of the computer is SDR1. That's what is called SDR1 is the one that has audio problems.
How long does this workshop run to?
It's 5 sessions of around 3. So that one.
You told me, and you said your email.
Okay, so let's start with FM. So basically, a VCO, if you think about it, a VCO, it could be think as a FM modulator because when we change the amplitude, these guys change the frequency, and this is what is FM does. Okay, basically modulate that changing on the amplitude with changes on the phase. Okay, so that's why it's interesting to think about it a little bit because this will help us on the, let's say, modulation part of the FM. So if this is the VCO, okay, we have some signal that is coming in. Okay, it will be some constants factor that is called like the sensitivity of the VCO. So how much frequency will change related to how much is the amplitude change. This is what they say here. Okay. Then will be the integrator part that we know that is on the VCO that will have some estimation on the phase. Okay. And this guy is the base frequency of the quotient frequency. Okay, the fixed frequency. So here we have the fixed frequency, and here we will add in how much that frequency will move. Okay, to make the modulation. Okay, related of course with this signal here. So we just add, make the cosine, and voila, we have our frequency modulating signal. Okay, this is all the same that we saw before. Okay, the estimation is the estimation of the error signal, but if we replace this signal, now is this one, 2 pi k is the constant, yes, times the signal, so we are here. So this one is just the output of here, this is the estimation, and the cosine will be, of course, this. So for sure, we don't want to write all of this, so we will start seeing this, okay, like theta FM, that's indicate how much the phase is changing on that frequency. Let's see, if we have that information signal, that is some cosine, okay, and we know that this will be our modulation signal, so if we made the math on all of that, so we see that the integral of that will be the sine, we follow all the steps, and we will arrive here. So I want to stop here. So basically our modulated signal will have something that have some delta F there, that if you remember, that's depending on that number will be if the frequency is a narrow band frequency or a wide band frequency. Okay, that is telling us how much I am allowing this modulation to move from the, let's say, my center frequency. Okay, this is that delta F here, and this IFI is the instantaneous frequency. So how much this changed from this one. Okay, this relation, all of this relation, is what it's called similar to the AM. In the AM we have the index modulation that will remember what was the index modulation on AM. Okay, if we change the index modulation, it will change how the envelope will move. Okay, so in the same case here, if we change this modulation index, it will change how far or how close will be the maximum frequency for the center one. Okay, so how much that FM will move. Okay, so if you don't remember too much about FM, what FM does is something like this. Let's say if you have a signal here, okay, so for example, when the frequency go up, this will be something like this. When the frequency goes down, it will be something like this, and then again this, and so on. Okay, all with the same amplitude, because it's not amplitude modulation, it's frequency modulation. Okay, that is what I am talking. Okay, these frequencies, okay, how far will be from our center frequency, okay, or our instantaneous frequency or base frequency. Okay, So at the end, our modulated signal will look something like this. So you could see that here inside, okay, we will have some information that we want to recover. So these are the two types. You should see this on some communication classes. There are two types of FM, the narrowband and the wideband. So the narrowband is when the modulation index is much smaller than 1, and the wideband is when the modulation index is much bigger than 1. Okay. So if we have our signal here, that will be the modulated signal. Okay, and then we apply this quadrature modulation here. Okay. So we will end with this factor, this one, and that one. But what happens if this, okay, is much smaller than 1? So we can approximate this to 0, okay, because it's much smaller than 1 multiplied by whatever will be much smaller than 1. So that's why we can approximate this part to 1, and we can approximate this part because this will be the angle, as we was talking before, that when the angle is really small, we can approximate the sine to the angle. So that's why we just take this part. Okay. If we move back again there, and our narrowband frequency modulating signal will look something like this. Okay. So if you take a look on this and do this multiplication stuff that will be at the end in addition, you take a look on this and you can tell me what this look like. This transmitted signal, what does it look like to you? Something that we saw last class. So we have some frequency component here, and then we have like one component going on the carrier and one component going down the carrier. So if we represent this, is this one, because we have this minus here. So this doesn't look like too much to this. It is, okay? So this, it was. We place a plus there. It will be an AM dual sideband transmit carrier, okay? So what I'm trying to tell you that a narrow band FM modulation, it looks like, okay, its spectrum, it will look like something similar to an AM dual sideband transmit carrier, okay? With the difference that we have this minus there, okay? And what happened in the case of wideband? So narrowband is usually used, on this kind of, let's say, remote controllers, walkie-talkies, whatever that is on ISM band, that is simple stuff, on-off, or things like that. Well, you will have some narrowband FM because it's really simple to implement. Okay, and it's really cheap. Okay, so wideband FM. Where we could find wideband FM? Where is wideband FM? Okay. Where? In which device, electronic? Where? Some idea? Cars? In which part of the car? The radio, of course. All the radios, all the FM radios are wideband FM. Okay, so that is the main application of wideband FM, is radio. Okay, so because it's really massive use, it has some regulations. Okay, so one of the regulations says that the maximum deviation that you could have, that delta F. So it's 75 kilohertz. So the maximum that I can move from the center is 75 from each side. Okay. And the maximum bandwidth that each FM could have is 200 kilohertz. That's why if you search on the dial, on the FM, you will see that every 200 kilohertz there is a new FM. Okay, that is why it's 0.7, and then, or let's say 0.3, and the next one is 0.5, and the next one is 0.7, and go on. Okay. So, well, the problem with the wideband FM is that it's not as simple mathematical representation as the narrowband, okay? Because we don't have any approximation on these two guys, okay? We cannot approximate that to 0 or 1 or whatever. So there was some mathematician, was the Bessel. I don't know if you remember the Bessel functions. Well, this guy was trying to do is to try to express this function by some formula like this, when these guys are the Bessel coefficients, and depending on the amplitude of that guys, you will see how much is the power that you will have on that frequency component, okay? Basically. So there is a lot of theory behind that, but this is how you will represent, let's say, if you want to see the spectrum. So what I'm trying to tell you is that the spectrum, if you want to see the spectrum of an FM, is not as clear to see in a spectrum of an AM, okay? That's why you see just in a spectrum that is moving 200 kilohertz, okay? But you cannot even see any, let's say, particular tone there, because there are a lot of them, okay? This could be really big. So that's Bessel functions. It will give you something like this, okay? Our now wideband FM modulated signal. We will have this kind of expression that can continue, okay? But basically, if you are transmitting some tone and modulating that with FM wideband, you could try to see something like this, okay? You are not seeing this, but anyways, it's mathematically is that way to see it. And then we need to figure out how much is the bandwidth, because as I told you, that's Bessel functions could run forever, but we have to make some cut and say, okay, I want to consider just this one, because it's the one that have power, the other one have really low power, okay? So basically, the bandwidth approximation could be something like that, 2n f, where n will be how many of these coefficient of Bessel function you have. Usually, you don't know, okay? You don't know how many. So this is some approximation, okay? That's taking into account the modulation index, that's one. And this is a really, you should remember this name. The Carson rule was the guy that say, okay, let's estimate the bandwidth of this way, okay? So we remember the modulation index was this. So at the end, if you see this number, this is 75, okay? So you have 2 times 75 plus 2 times the what? The maximum frequency, okay, of that bandwidth. So that is where that 200 kilohertz came from, because you have 75, so you have 2 times 75, and if I don't remember, yeah, the maximum frequency that you could transmit is around 65 kilohertz. So this gives you something like 256 kilohertz. So this number will be the real bandwidth, of the NFM, okay? But then you say, you should think, okay, this is the real bandwidth I am transmitting. But under regulation, tell me that I cannot transmit more than 200. Okay, because we already said that it should be 200. So what's gonna happen here, maybe you don't remember, but for sure you should see this. So let's say the real spectrum is this guy, but what I am allowing to transmit is just this guy. So this is 200, and the real one is 256. So we are like attenuating these high frequency signals, okay? So in order to solve that, I don't know if you remember, there was something called pre-emphasis and de-emphasis, that is to solve this situation, okay? Okay, use that pre-emphasis, the emphasis, because we want to listen some radio, and all the radios are doing pre-emphasis, okay? And well, we have to do the de-emphasis in order to hear it. Well, but first, before to go there to hear some FM, we need to know how to demodulate that FM, okay? So, let's say this is our signal, okay? Our signal that is on the air. And if we think about it just on a mathematical way, if we differentiate that signal, this will be the signal that we will have, okay? So we could see that we have some part of the signal integrated here that will have some high frequency component because we are adding frequency here to that cosine, so this can be moved by some low pass filter or something. But the cool stuff that if we just make the derivative of that, we get this part, and that is our signal, okay? So the idea is to try to see how we make some derivation stuff to get our signal back, okay? Basically, this is what will happen, okay? If you make the derivation of this, you will get something like this, and we know that with some envelope detector, we could detect that signal. Say, okay, but the envelope detector was for an AM. Yeah, but if you do that, you can recover FM signal, okay? So we will try to continue on that. So what we are sending through the, let's say, SDR, USRP, or whatever, will be this signal, but remember that we are sending on quadrature, okay? So we have to multiply by this complex representation there. So at the end, what we are sending is this, okay? If we made the math on that, go with the low pass filter that we have inside, we cancel the high frequencies, we can get with these green two guys, okay? That is something that I place here. So, if we come back again to our complex representation there, what we are giving at the input, okay, to the SDR, it will be something like this, okay? So, if you take a look on this, when we make that derivation stuff, we will need to try to find for some angle here, okay, on the receiver, just to give you an idea. Well, and again, this will never be zero because we will have some issues with the two receivers. So this is again the same picture that I'm showing again and again of the offset on the frequency. So the signal that remember, maybe you get lost. This guy is the one that we have to receiver, okay? So on the receiver side, after making the modulation, because we make the down conversion with the IQ, so this is what you have at baseline, okay? After receiving at the output here, you will have that kind of signal, okay? So let's see. We derive, let's say, the I branch and the Q branch. Okay, so if we make the derivative of that, we get this and this. Then it's quite long the procedure, but just try to keep focus here. So we make first a derivative of the two branch, then we mix the one that we make the derivative and the other one this as it is. So here we mix them. We get this one, and at the end we subtract these two results, this one and this one. And believe me, this is like 2 or 3 pages of math stuff, but believe me that at the end what you will have is this, okay? So if you remember, this guy was an integral of our signal. So if we our derivative an integral, we get our signal, okay? So maybe this is much clearer for you, because now I am trying to turn you like a hardware guy, it's not too much software. So this is a real implementation, so try to think what we already saw in the formula. So this is the complex signal that we receive. again, these two delays is just for the signal at this time arrive all together at the same time. This is simple differentiation stuff, mixing, and I didn't talk about this part, okay? We just show you all of this, okay? Just the mixing and the subtraction there. But what happened is that we have this factor that will be like a DC component, so that FM recovered FM signal will look like something like this, okay? And we want this signal to be here, okay? So that's why we have to normalize in some way. So in order to normalize this guy, we just square, take the magnitude basically. This is a way to take the magnitude and just divide there. And you say, oh, okay, this could work fine, but as you could see, this is quite simple, but it is not as simple to implement in hardware. Okay, so this differentiator stuff or the modulator is good to learn about the theory, but it's not as good to implement on real hardware. Okay, so we will see that the real receiver or the modulator that we will implement have this theory behind, but it's have a better way to implement it. Okay, this is just if you implement each formula as it is. Okay. So this will be the way that we will implement it our receiver. Okay. So remember that on the complex representation, what we received after down conversion, it was something like this without this delay, of course. So, but what's going to happen if we just make simple delay here? Okay. And on the same signal, if we have a phase shifter, so 100 degrees, 180 degrees, that is just complex conjugate. It's really simple stuff to do it. Okay? So we take the complex conjugate of that one. So this will be the result and that will be the result. Okay? If you mix it, what is the mixer? It's a phase detector. We saw that the mixer acts as a phase detector. So we want to see the difference between this phase and this phase. Okay? So this is something that I grow here. Okay? So we want to take the difference between this phase and this phase. Okay? And at the end, we will see that doing that, we will have our signal recovery. And as you could see, well, forget about the magnitude, you just take the angle, so we are taking a look on this to recover our signal. Okay? And as you can see, the implementation is quite simpler. First, there are no division. Okay? That is really hard to implement on hardware. And it's just a delay and a phase shifter. Pretty much easier to implement. Okay? So, if we continue with all this formula stuff, so we take the angle, we care only about this. But what happens if this delay, as they say there, if that delay is really small? So, when this delay is really small, we know that this approximates to the derivative. Okay, that's why we say, okay, this is like the derivative. And the same on this, if the phase difference is really small, it will approximate to some derivative stuff. If you remember, the differentiation results was this one. Okay, exactly the same. So we arrive to the same result, but much easier in hardware implementation. Okay, so we take the derivative of this and we will recover our signal. Okay, so. But this one is the one that we will implement on the SDR, okay? The other not, because it takes more. Anyways, nobody implements on that way. It's just to give you an idea where the theory of this came from. And the last, let's say the last. So we have the differentiator and the phase shifter, and you could see like a third. The modulator, that maybe you did this on some analog FM lab. I don't know if you did it, but in an analog FM lab, what you do is just to have a VCO as a transmitter, okay, and a PLL as a receiver. Guys, basically, that is how analog FM works. Okay, if you sometimes take some lab. The problem with this, what will be the problem with this PLL? So, basically, what a PLL does, try to follow phase of change. Changes on the phase, sorry. Changes on the phase. But what happened? This guy here, it will never be quiet. It will always moving because it's an FM modulator. Okay? So the problem with this PLL, let's say, is it will never get locked. Okay? It will always trying to capture. Always trying to capture. So here, we will have that phase difference so we can recover the signal. Okay? We are not implementing on this way because that's the analog way. But just to give you an idea. And this is what I was talking about here. Okay? There are two standards like the US and the European. So there are different ways to implement this. This is implemented as a filter, as a delay on the filter. So for US it's 75 microseconds, Europe is 50. But what is important here is this free emphasis that you remember for what it is. Because we are attenuating these frequencies here, okay? Then we have some kind of amplifier to give some better response to that frequency. And on the receiver side, of course. Okay, so we amplify, and then on the receiver side, we take into account that amplification. You remember something of this, or you don't remember? You should remember something. Okay, and this is the how actual FMs are. Okay. At the beginning was just mono. Then when stereo came, these guys know that the better way and cheapest way to get the signal back is to have some tone there to recover it from. So that's why they are transmitting. This is actual, so you will see how actual FM is working now, and you will see you should see something like this. Okay, you should see some spectrum here on the mono, the tone. But take a look on this tone. This tone, this is the double of this one. And this guy is the double of this one. 3 times of this one. Okay? So just to give you an idea that all these frequencies is recovering from here. Okay? And this one is what you saw on the you see on the display of the radio that say what is song is playing or what is the name of the radio. Okay, this is the radio data system that some radios has it, all radios doesn't have it. Okay. So the idea now is we want to try to capture this and listen, and on another lab we will try to send one audio here and one audio here. Okay, so you should listen on one speaker one music and the other speaker another music. Okay, because we are sending 2 channels at the same time. Hopefully you will hear something. Well, this is how we will implement this. Okay, we will have some LO or carrier frequency here. We will just multiply by 2, by 3. In our case, we are not using this branch. Okay, we are just sending left and right. Okay. So here, if you add all together, it will show you the spectrum that the previous slide showed before. And on the receiver side, this is let's say the transmitter. And on the receiver side, that is the most interesting part. Here, you will see on the lab that here you will have a very notch filter, okay, to capture that 19 kilohertz tone. Okay. So when we recover that tone, here, okay, we will have a PLL, okay, that will try to follow this tone. And here we will have another PLL that will try, this guy will try to follow this PLL. So it's just one PLL following, and the other guy is following the double of the previous PLL. Something like that is how you implement it. And basically, of course, the 2 bandpass filters for the left and right. And you recover the signal. So we will not use this part, okay? We'll just recover the, so we will have mono here and left minus right here. So if you combine it this way, you get double the right and double the left. So this will be on the transmitter side, okay? So if that is our baseband signal, so we was talking a lot about this representation here. But then we are giving this signal to the USRP, so we are keeping this I and Q component, okay? So at the end, if we made the math, it will bring something like this. So what we are really transmitting is this signal, okay? But this K USRP will be the game that you play there, 60, 70, or whatever, it's just a game, okay? So this number is just a game, but what is important here is this is the signal that we are transmitting. And remember on the baseband, what we did is this part of the signal with down converter and do all the stuff, differentiate. In our case, we are not differentiating, we just phase shift and delay, and you will record the signal. So one of the things that I will tell you is that the let's talk about that on the lab better. So if you remember the first slide that I was talking about how a VCO could be an FM modulator, that VCO have this architecture, okay? That is the one that we want to use, okay? So we have the signal here, just this is the sensitivity of the VCO, okay? So we are doing this, okay? Plus some constants factor that will give us this, the base frequency. So remember that here we are adding the base frequency plus the frequency that is moving, and that frequency that is moving is related with this information signal, of course. So this one will be this architecture here. It will be how we implement our modulator. So if you follow, this is exactly the same like this. Okay. So this is this box. Okay. So here we will have some audio stuff. We will resample to reach the DAC sample rate, whatever. And this will be our FM modulator. Okay. And then the SDR. And on the receiver side, forget about the digital data because we are not sending any digital data for now. So that's why that branch is not there. So what we will have is this guy that will, at the end, will be a PLL. This just has double of this. And we're recording this in this way. So this go inside, let's say, this box here. On the sorry. This is transmitter side. I get wrong. This will be how you will combine the left side and right side here on the encoder, and then send it to the modulator that we saw on the previous slide. Okay. So that's why here you will send some audio and here another audio. You will combine here, transmit. On the receiver side, you should listen different audios on different speakers. That's the idea. Okay. And this is the modulator. Okay, that is quite simple. The most interesting stuff, we will take a look a lot on this part. Okay, how we record the tone and make the PLL works. Because the rest is just once that we recover this, and we know that we have to be here and filter this is the easy part. Okay. It's not that easy, but it is. And on the spectrum analyzer, you should see something like this. Okay. For sure, you will see this. This may be not too high, and you should see some difference between this and this on amplitude. I mean. So remember that mono have almost double amplitude as the stereo one. Okay, guys. Let's do some coffee now, and we will start because we have like different practices to do. So, okay.